Desligar a imagem fixa, né? Também.
Pode, quando começar o colóquio, a gente desliga as imagens. Mas aí, na hora da pergunta, a gente volta.
Estamos ao vivo.
Hello, good afternoon, everyone. We have today one more colloquium of the Physics Institute of the Federal University of Rio de Janeiro. And today we have the pleasure to welcome Dr. Dario Rodrigues from the University of Buenos Aires. And I'll ask my colleague Carla Bonifaci to introduce him.
Okay, hi everybody. So it's a pleasure to me to introduce Dario Rodriguez. He studied at the University of Buenos Aires, and also he did his PhD as a student at the same university, but he was working in nuclear physics. He worked in the TANDAR, in the National Commission of Atomic Energy. And also he was working in this institution since 2005. During his PhD, also he spent 4 months working in Germany, and then he did a postdoc in chemistry. So he has a broad knowledge of science, of things. Now he is an assistant research at CONICET, and also is a teacher assistant at the Buenos Aires University. And I met him 1 year ago, about 1 year ago, when he was spending 1 year as sabbatical at Fermilab. And he went there to work with the Skipper-CCDs for the use of those detectors in dark matter, neutrino searches, and also he developed a big part of the use of Skipper-CCDs as quantum imaging, for quantum imaging. So this is the subject, the main subject of the colloquium today. Now he's back in Buenos Aires, and after this year that he spent, he started to work on mounting a dedicated lab for the Skipper technology at the Buenos Aires University. So thanks a lot, Dario, for coming here today in Zoom. Hope next time will be in person, and thanks a lot.
I also hope that. Thank you, Carla. Thank you for this presentation. Hello, everyone, and thank you to the organizers for this opportunity. I am glad to talk with you about the effort that we are doing nowadays to put this technology, Skipper-CCD, in different fields, as Carla already mentioned. So I will share my slides. Let me... Okay. So you are seeing my slide, right?
Yes.
Okay. So I am going to talk about this Skipper-CCD technology, but in particular during this talk, I will put focus on the quantum imaging applications of these sensors. Just like an overview of the topic that I will cover during this talk. First, I would like to give some details about the Skipper charge coupled devices sensors, and then to explain how by using one of the most important features of this detector, we were able to calibrate them in an absolute way. Then I will talk about how we are working on the implementation of the Skipper-CCD technology in quantum information science, in quantum imaging in particular, and then how we can use quantum imaging for the dark photon searches, also through the nonlinear optics. So let me start saying a few words about the charge coupled devices. Probably all of you are familiar with this technology. These are an array of coupled capacitors. They can move the charge in each pixel. Each pixel has, in our case, 15 by 15 micrometers, So we can move the charge between neighborhood pixels, and we can collect that charge. So let me just put an example. Suppose that you have a muon. Let's say a muon could be an electron, a photon, gamma, X-ray, a visible photon, also the elusive neutrino, and also the hypothetic dark matter particles. If any of them pass through this detector, which we can think like a piece of silicon, these particles can produce ionizing electrons, and these ionized electrons, because of the field, the electric field we apply in the sensor, move to the surface, they drift to the surface, and they are captured into these pixels, these small pixels. One of these CCD usually has 4 million, so something like 4 megapixels, 6 megapixels. However, they are small sensors, just something to have a reference. Here you see you have a picture of one of them, and this is something like 2 centimeters by 4 centimeters, because again, each of these pixels is very, very small, which is one of the reasons why this sensor offers a very, very good spatial resolution. So how charge coupled devices proceed in order to measure the charge in each of these pixels. So if we expose the piece of silicon, what we call CCD, when one of X-rays, let's say, in this case, this cartoon is for an X-rays of 6 kV, when these X-rays interact with the silicon can produce a lot of electrons. For example, in this case, 1573 electrons. And we will also get some electron because of dark count, which is very, very low in this sensor, but of course we have few of them. If we expose a little bit more, another photon can produce a lot of electrons in another pixel. Of course, they can also be distributed around, but for the sake of simplicity, let me talk about this case. After expose the CCD, what we have is some number of electrons in each pixel. So we want to know the amount of electron in each of them. So the procedure is the following. We move all the charge in each of them down. So we move each row 1 position down. In that way, we get the charge what was in the first row, we get that charge in the serial register, and then we move the charge right in this example in order to reach the sense node. This red square here represents the sense node. The sense node is the place where we sense the charge. We measure how many electrons we have. I am talking about a general charge coupled devices up to now. However, what is new in the Skipper-CCD technology is what is going on there in the sense node. In the Skipper-CCD technology, you are able to move the charge between what we call the summing well and the sense node. And you can do that as many times as you want without destroying the charge. So in this cartoon, I am moving the charge 3 times, 1 to the sense node, 2, and 3. But we can do that again as many times as we want. So this process is the same that we do in a regular charge coupled devices. The extra point here is the Skipper-CCD can measure as many times as we decide the charge in the last step, which is the sense node. Okay, which is the result of doing that? Why this is good for us? As you know, if we measure a lot of time the same magnitude, if the measurements are independent, the uncertainty in the average goes like 1 over the square root of the number of measurements. But also, a different point of view of that is what I am trying to explain by using this slide. If you have a regular CCD, you need to measure the pedestal and the signal. Signal is when the charge is located at the sense node. If you are doing that, the high frequency noise can be get rid of because it's canceled between one cycle and the other one. But in this example, you see how a low frequency noise cannot be avoided, and you will have an offset because of that. However, in the Skipper-CCD technology, where you are doing that as many times as you decide for each of these pixels, you can avoid the low frequency noise because these differences are compensated when you measure again and again and so on. So again, the result of doing that is if you measure after doing, let's say, n measurements, you can calculate the average, which is mu here. So the variance goes like the variance of only one sample divided by n, which means that the uncertainty goes again like 1 over the square root of n. And here we can see the effect on the image produced by this protocol. If we have only one sample, again, this corresponds to the conventional charge coupled devices, which in general have a readout noise close to 2, 3, 4 electrons. What we see after taking one image is something like this. We are not able to distinguish which of these pixels are empty, which has only 1 electron, which has only 2, and so on. However, if we measure the charge in each of them twice, after measure again, we know, we need here, we know better which is the charge. Here we have the distribution of the number of charge in each of them. Let me say that here you have negative values, which is correct because what we are measuring here is the voltage in the sense node. So it fluctuates in the positive and negative values. But if we go and for 4, 16, and so on, you see how the redound noise is going down, and the number of pixels with 0 charges is now pretty well defined. It means that after doing here 4,000 measurement of the charge in each pixel, we know with excellent precision that all of them are empty, but only one has 1 electron. This plot is showing that the behavior of the redound noise as a function of the number of samples. When I said samples, I am talking about the number of times that we are measuring the charge in each pixel goes like 1 over the square root of n, because this is a log-log plot. So you see the slope of this plot corresponds to 1 over 2. Like an example, let me say if we start with only one sample with 3.5 electron, after doing, let's say, 300 measurements, we reach a sub-electron redound noise as low as 0.2. If you want to have more details about that, you can see this paper, which was one of the first papers where the people from Fermilab describe the general characteristics of these sensors. So what we can do using Skipper-CCD technology? As you can imagine, there are a lot of fields that can take advantage of that. One of them is the dark matter searches. Another one is neutrino physics, also in astronomy. And the one which is the main topic in my talk, which is the quantum imaging science. But let me just say a few words about dark matter and neutrino physics, only one slide for each of them. About dark matter, there is a collaboration, which is called Sensei. This collaboration is using right now and Skipper-CCD. So in fact, this is the reason why the Skipper-CCD exists. These guys developed the technology aiming to search for dark matter. So this detector is at Fermilab, 100 meters underground. And here is Javier Tiefenberg, one of the developer of this technology, making some changes in this setup, which is Sensei. Is the small version, the Proto Sensei. But this small version, which has a CCD, which is only 2 grams of silicon, has today the best exclusion limit for light dark matter. You see here, this is from an article we published this year. You can see the whole manuscript looking for this archive. It will be a PRL, but it's not published yet. So something that is amazing here is the other experiment looking for dark matter in this range of mass are, for example, xenon 1 ton, which has a very, very nice result, but they use 1 ton of material. Here we have only 2 grams. And of course, we are working on the 10 grams experiment, and there are another effort looking for 1 kilogram of Skipper-CCD, which is called DAMIC M, and the next step will be Oscura. Oscura will have 1 kilogram of Skipper-CCD. Again, each of them is roughly 2-3 grams, so it means 4,000 skippers. It's a challenge. Okay, the other field, which is a very, very active field today, is the neutrino physics. We are working on a future experiment based on Skipper-CCD technology to observe the neutrino interaction using Skipper-CCD technology. So one of the main interaction today regarding neutrinos is the what we call 7. 7 is coherent elastic neutrino nucleus interaction. It was observed for the first time a couple of years ago, just a couple of years ago, for only one experiment, which is called coherent. But it was predicted by the standard model 40 years ago. So we can see, we are planning to do this experiment to see coherent in a couple of weeks with a 90% sensitivity. So this experiment will be something great in neutrino physics, but not only because of the standard model interaction. We are working on the determination of sensitivities for beyond standard model physics in neutrino field. And the prospect we have for neutrino interaction through the magnetic moment, for example, light vector mediator, light scalar mediators, and all the new mediators you can imagine, and the theory can discuss, and they are agree about some benchmark model for neutrino physics. Okay, for all of them, we have a very, very good prospect doing this experiment with the Skipper-CCD in a nuclear reactor. We are thinking in Atucha 2, which is a power plant of 2,000 megawatts in Argentina. If you want to go more about Violeta, this is the name of the collaboration, you can visit this webpage. So only one slide about neutrino, only one slide about dark matter, because the main topic of my talk, as I already said, is quantum information science. Let me talk about one detector. It is only one case because we have a lot of them and they have different features. But in general, as I already said, they have 4 megapixel or 6 megapixel. Each of them is 15 by 15 micrometer. The thickness of these detectors can be 200, 600, 675 micrometers, no more than that. It's a very high silicon resistivity. The dark current is pretty low. This is not the best value. In Sensei, for example, we can reach the 10 to the minus 4 electron per pixel per day, which is, by the way, the best, the lowest value even observed like dark current in a sensor. This detector must operate in a 120, 140, 160 maybe Kelvin degrees. And again, the same example as I already mentioned, for only one sample, you have a conventional CCD with 3.5 electron per pixel per day. So electron per pixel. But if you go to 300 samples, you can reach sub-electron reading noise. This is how Skipper-CCD looks like when it is inside the doer, because it requires vacuum. Also, we need to reduce the temperature until reach 140 Kelvin degrees. Something important to mention here, what you are seeing over here is the LTA board, which is a low threshold acquisition electronics completely designed for these sensors. So how does an image taken with this detector look like? So here you see a lot of white dots. The most of them are produced by X-ray, because this is an image of the skipper after expose the CCD with X-rays. However, we cannot avoid the muons pass through the detector, and they release energy and they produce ionizing electrons. And this is what you are seeing here. This is a muon. Here you have another one. Sometimes you have a muon pass through the complete surface, the complete bulk, let's say, and then you get a very, very straight track on the surface after the charge drift to the surface. And sometimes we can get an alpha particle which produce a lot of electrons, and there are another little dot that can be explained with different processes. Okay, how we process these images in order to see something regarding to science. So first, in quantum imaging and also in some nuclear physics applications, we are interested in knowing the relationship between the ADU. ADU is the analogical to digital units in which we measure the charge in each pixel and the number of electrons that is exactly in that pixel. So what we did is expose the CCD to a LED, and changing the time of the exposure, changing the exposure time, we can produce different number of electrons on the surface of the CCD. We can populate the pixels with a different number of electrons. In that way, we have a lot of images with a different number of electrons, so we are able to see how the number of ADU increase as the exposure time of the CCD increase. So the higher the exposure time, the higher the ADU, of course. Then we can pay attention in some small region of this plot. And thanks to the capability of doing a lot of measurement of each of them, as I already mentioned, we can distinguish between 0, 1, 2, 3, and so on electrons. And something amazing here is we can do that not only in this regime, which we have less than 10 electrons. We can do that also if we go to a very high number of electrons per pixel. Here you have 1572, 1573, 1574, which are produced, for example, for the X-ray of 6 keV, and we are also able to distinguish between them. So we can assign each of these to a number of ADU without using any reference value. This is the reason why we are talking about an absolute calibration. So after doing that, we know exactly which is the relationship between the ADU, which is the number we get from the amplifier, and the number of electrons in each of these pixels. So after doing this calibration, we expose the CCD to X-rays coming from the iron 55, which produce, in general, charge around 1570 electrons. And after fitting these peaks, we were able to measure the mean number of electrons produced by one of those X-rays. Then, dividing the number of electrons by the energy of these X-rays, sorry, in the other way around, we get this number, which is the energy to create an electron hole pair, which is a very, very important number, not only in nuclear physics, it's important for neutrino physics, for dark matter research, because it's what you need to convert, what you see in the detector when you need to convert the number of electrons in some amount of energy. And we also determine the Fano factor, which is the relationship between the variance of the charge distribution and the mean value of the charge distribution. If you are interested in this kind of work, you can see this paper on arXiv. And let me say that Skipper, again, can produce very, very good science data because this result has the smaller sensitivity ever, the smaller uncertainty, sorry, ever. So now we are ready to go into the details of what we are planning, like the quantum information science program for the Skipper-CCD technology. Let me start talking just a little bit about the spontaneous parametric down conversion process. Probably many of you are familiar with that, and some of you are expert on that. I'm not an expert, but I will try to describe this process. So if we have a laser and the photon from the laser interact with a nonlinear crystal like the BBO, which is one of the most typical crystal used for that, there is a small probability. When I say the small, I am talking about 10 to the minus 8, 10 to the minus 9 probability to produce a pair of photons. Instead of one, we have two. And because of the energy and momentum conservation, those photons are correlated. So if we measure one of them, we are exactly where the other is. And if we measure the energy, we have the energy of the other one. In particular, if we are looking for the photon that are carried with the half of the energy of the pump photon, if they have exactly the same energy, the half of the energy of the pump, again, we expect they have exactly the same angle with respect to this blue line. So if we project these correlated photons on a surface like the CCD surface, we expect to see rings. I am talking about correlated photons, twin photons. I can say entangled photons. However, entangled means a little bit more, and entanglement is not necessary for the application that I am talking about. It's necessary in other case, but let me say correlated. But if you have knowledge about the entanglement of photon, you can think in this picture in order to go with this procedure. So this is the process we use to create correlated photons. And how we produce that? Okay, this is the system we have at Fermilab. Of course, we need to cover all of this, in this case, with the black box and then a blue box. And inside the blue box, we have this small system, which is the one produce the correlated photons. We have a laser of 405 nanometers, and then a BBO, and the BBO produce a lot of different wavelengths, but in particular, we will select the 810 nanometer. You see, this is the double of 405, which means the energy is exactly the half of this energy. So we expect two photons with this wavelength, two photons with the half of the energy of the original one. And then we expect those photons be detected by the Skipper-CCD, which is inside this box here. Here you have another picture of the same, the laser, two mirrors, the BBO crystal, which is the nonlinear medium where the spontaneous parametric down conversion process takes place, and then a filter, and inside the Skipper-CCD, here on top view of the same system. So after the BBO crystal, the nonlinear crystal, we have this cone which will be projected on the CCD. What we got after doing that is what you are seeing here. So this is our experimental result. And each of these rings correspond to pairs of correlated photons. It means if you have a photon here, you have a photon in the opposite side. Of course, that is not completely true because we have inefficiencies. Some of them cannot arrive to the detector. We have inefficiencies. However, what we expect in the ideal case is the same number of photons from one side to the other side. And something really nice here, that we are not only seeing the maximum, which is here, we are able to see some secondary maximum, which means that the sensitivity here is pretty good. So first step, we see the rings. Second step, we want to see correlation. So what I am talking about when I say correlation, we have taken 100 images of this ring, 100 images. This is the same as before. So here I have a different scale. This is the reason why you are not seeing different secondary rings, but this is exactly the same experiment. If we have taken 100 images and we have measured the number of electrons, which means the number of photons. Sorry, I didn't mention before, but in this wavelength, in the visible range, you get 1 electron per 1 photon. So we can count the number of electrons and we know how many photons arrive. And we did that for 100 measurements and we produced the histogram. This histogram is the number of photons in each of these samples, in each of these pictures, images of entangled photons. And here we have the same 100 images, but here we measure the number of photons inside this box and we produce the histogram over here. Then we define a random variable, because of course this is a random variable and this is also a random variable, but we define a third random variable as the difference between the number of photons here and the number of photons here. And we produce the histogram here. This is what we expect if they are not correlated. Why? Because the variance of the sum of the two random variables is the sum of the variance of each of them. And the difference between, so this random variable is defined as the difference between them. So the random variable has a variance, which is the sum of each of the random variable you have subtract in order to get it. But as you are probably thinking, we are not interested in seeing correlation between this point and this point, because we know the correlation is between this point and the point which is in the opposite side by the spontaneous parametric interconversion process, which is the reason why we have this ring. So we move this spot over here and we perform exactly the same analysis. So we measure the number of electrons in each of the 100 images inside this spot here, nothing changed. And then we measure the number of photons inside this box here. But something changed a lot. This is the variance of the difference between the number of photons here and the number of photons here over the 100 images. So we have a variance for the difference which is smaller than the variance of each of them, which means they are correlated. So we have observed correlation in this simple way, but we know we can do that better. Better means that we can look for angular correlation. It means we can measure the correlation between the photons that arrive in some small slide here, for example, and compare the difference between this number of photons with the mean value and the difference between the number of photons here and the mean value. And we can do that theta by theta. We can go around this ring in order to find correlation in the angular distribution. After doing that, we can start with a different theta 0, which is the reference for the first correlation. And we can do that all around these beautiful rings. After doing that, we have this function. We describe the correlation the angular correlation between all the photon produced by spontaneous parametric dot conversion. And this is the result we got. This peak over here means that at 180 degrees, we have more correlation than in the other angles. This is what we expect. This was produced dividing the rings in 120 slides. But something to say here is, okay, this is really nice. However, the correlation is not so strong. We have a lot of reason to explain why this correlation is not so good, but the main reason is we have different optical steps, filters, the glass of the dual, the inefficiency, which is pretty small, but it's not zero in the detection efficiency of the Skipper. So there are a lot of reasons why this pair of photons cannot arrive together. They cannot arrive together all the time. So we are losing correlation. And this is the reason why we are seeing this nice peak, but not so strong. And we are working on improve this correlation. Why we are interested in correlation? Because the correlation is what we need to go the next step, which is go for quantum imaging applications. So how the Skipper-CCD can contribute in quantum imaging? Because up to now, it was not necessary use the Skipper capability. However, we may compare this technology with the technology that already exists. This is not a competition. There are very, very good sensors. One of them is the electron multiplier CCD, which is able to measure the number of electrons that arrive to each pixel and distinguish between 1 and 2, and probably between 2 and 3, and probably between 3 and 4, but no 4, 5, you see. It's impossible to go above 3 probably. But there is something good in this detector that is not so good in the Skipper technology. This is the time resolution. I told you guys that this detector reach this sensitivity after doing a lot of samples, but each samples need time. It's just microseconds, probably milliseconds, depending on how many samples you decided to make. However, in total, if you are interested in read out the full CCD, 4 megapixels with 300 samples, probably you need something like 1 hour. So essentially, we don't have time resolution, but we have this such a beautiful peaks. So there is a place where Skipper-CCD can help us to make something with quantum imaging. Okay, probably the most famous application in quantum information science is what the people call ghost imaging. For ghost imaging, in principle, we need time resolution. But if we are interested in measuring the absorbance of this object, we don't need time resolution. Suppose, again, we have a pump beam which interact with the crystal, and after the crystal, we produce a twin pairs of correlated photons. If one of them pass through an object and the other one goes through the detector, there is something that we can avoid by using the information of the entangled photon. In general, when you measure the absorbance of one sample, you need to interact by using photons, and you can estimate, you can calculate how many photons you are sending to the object. However, this is a Poissonian random variable, which means you have an uncertainty in the number of photons you are using to sense the object, which goes like the square root of the number of photons. However, in general, it is called shot noise. But if you are able to measure the number of photons that you are using to measure the absorbance, for example, using the partner, which is correlated, you are able to avoid this uncertainty, because you know exactly how many photons are here, which means you know exactly how many photons interact with the object. And then you measure how many photons pass through the object. And as the ratio between this number and the other one, you can get the absorbance with an error which is better than the classical limit. When I said classical limit, again, I am talking about the shock noise produced by the Poissonian nature of the random variables called number of photons. So if you have only one photon per pixel, probably I suggest you use one of these detectors, because if you have only one photon per pixel and you have time resolution, you can make, for example, ghost imaging. If you have 1,000 or more than 1,000 electrons per pixel, you don't need an Skipper-CCD, because if you have, let's say, 10,000 electrons, the uncertainty, if you think this number as a Poissonian random variable, is 1%. So 1% is so good, probably you can see correlations. But in the intermediate range between 2 free electrons and until, let's say, 1,000, this is a range where the Skipper-CCD have something good to offer. And we need an estimator which doesn't depend of the time, because essentially, as I said, we don't have time resolution. We have, but it's very, very poor. So this is one way to measure the absorbance by using this estimator. N1 here is the number of photons in one branch, N2 is the number of photons in the other one, and delta N2 is the difference between this number of photons and the mean value. So this estimator essentially propose use the entangled photon or the correlated photon to subtract the noise in the other beam. So we can do that, and we are planning this experiment as the first quantum imaging application of an Skipper-CCD, and we are planning that in our lab. I will tell about that in few slides. So I know that Warburn is connected. I saw him, and it's an honor to me to tell you about this technology. And Warburn, you said that ideally the detection system would consist of either two-dimensional multi-detector arrays or a CCD camera with single photon sensitivity. Okay, a Skipper-CCD is a CCD camera with single photon sensitivity. And other experts, like Steve, they agree about the importance of a two-dimensional detector array with even lower noise. Again, this is what we have when we are talking about an Skipper-CCD. Two more comments about that. Low noise and efficiency two-dimensional detector array are essential in the use of a spatial state in quantum communication and quantum information processing. And Moreau, which is the author of the paper I already showed you with the estimator for the absorbance, again, more efficient photon counting cameras, very low noise are the future of quantum imaging scheme. I think, I am convinced that Skipper-CCD are the future in this sense. For this special regime is not a competition with the other detectors, because when you need time resolution, this is not the best option. When you are interested in seeing only one electron, this is not the best option. If you have a lot of electrons for node, this is not the best option. But if you are in the middle, probably Skipper-CCD is the best option. And my last slide, are you there? Can someone say something?
Yes.
Okay, you are still there. I don't know how many are you, because I am not seeing the list of people connected, but I will finish in a few minutes. The last thing that I would like to talk with you is how to use a nonlinear medium, essentially the same spontaneous parametric dark conversion process, for looking dark matter. If you have a pump, again, and it interacts with the nonlinear medium, we have the spontaneous parametric dark conversion process. But if the dark photon exists, the coupling between the dark photon and standard model photon is a window to produce dark photon by using this technology. This is the general overview, but something very, very important here. Even if signal and either photon have exactly the same energy, here we are not expecting the same angle. There are two reasons why we are not expecting the same angle. First, because the dark photon carry with mass. You know, dark matter, dark photon need mass to explain all the astronomical observation we had to propose dark matter. And the other thing is that the interaction between this dark photon and the baryonic matter is so weak, which means that this dark photon has a refraction index like that we can consider equal to 1 in a very, very good approximation. So they don't see any material and they have mass. These are two reasons why we expect the photon have a different angle that its partner, even if they have the same energy. So this is the Lagrangian we need to propose to treat with dark photon. This is the general way in which in QED we describe the interaction between standard model photons, and here you have essentially the same for dark photons. This is the term we need to have mass mass in the dark photon, and this is the coupling between the dark photons and the standard model photon. If you do to the Feynman diagrams, you have the spontaneous parameter in conversion, the process we were talking about, but you have the dark, we call dark spontaneous parameter in conversion to this process, where you have a standard model photon which produces two photons. One of them is a standard model photon and the other one is a dark photon. This dark photon has a coupling which is called epsilon here, is the same epsilon you have here, that explains which is the probability to create a dark photon by means of this process. Of course, you have higher orders, but we are not interested in because the probability to observe this process is pretty low. You can imagine that these processes are out of the scope of any experiment today. However, here we have an opportunity to look for dark matter through nonlinear optics. So Matthias Senger was the guy working on it at Fermilab with us during his master thesis. And he developed a model to describe a spontaneous parameter conversion, and we compare this model with the data. And you see that we are able to reproduce what we see, and the reason why the model is so good and the reality is not so good because we have background, and we have a lot of effort on reducing that background. But we are in the good way. So now we are able to put mass and describe what we expect if we can produce dark photon by using dark spontaneous parameter in the conversion process. If we choose a very convenient material with some special characteristics, I am not going into detail here, but there are a lot of parameters that we must consider when we want to find the best material to do that. We also can get the phase matching in a condition where the dark photon production is enhanced in comparison with the spontaneous parameter in the conversion. Let me say that here we don't have the probability coming from the coupling, which is the number we want to constrain. So this in the reality will be order of magnitude below that. But if you have the same coupling for dark process and the standard model process, you will see something like this. This is not the real example. This is the theoretical approach. So we are working on it in order to have a realistic proposal, and we are also calculating which is the sensitivity for this coupling, so the coupling between dark photons and standard model photons, as a function of, sorry, this is in Spanish, but you can understand this is the mass of the dark photon. And as you increase the mass of the dark photon, you decrease the coupling, so you can exclude until 10 to the minus 4. This is not competitive right now, but let me say that is not competitive, but we have more things to take advantage. For example, you know, where you have a dark photon, the dark photon carry with mass because of described by this term. If you have mass, in contrast with the standard model photon, you are able to have a longitudinal polarization. So this is a very different feature, and we can exploit that in order to get rid of the standard model photon and just looking for the dark one. The other things is that the standard model photons, when they are produced, they are in coincidence, they are twin photons, and they arrive together. So we can use the coincidence with enough time resolution. I am not thinking about Skipper-CCD right now, to say, okay, if we have two photons, we know they are standard model photon, because if one of them is a dark photon, we cannot see it. So we can say, okay, all photons that arrive together can be get rid of, and we are analyzing only the photon that arrive alone. If we have a photon alone, we can see the angle of the photon, and we can speculate about who was its partner, probably a dark photon. Okay, my last three slides are just to comment that we are in the process of building a laboratory in the University of Buenos Aires in Argentina. The name of this lab is Lambda, which is the acronym for Argentine Laboratory for measurement of with very low threshold detection and its applications. So we plan to have two cryo. We need cryo to refrigerate, to go down the temperature of the Skipper-CCD. We are buying single frequency lasers, turbomolecular vacuum station, because I already mentioned we need to have these sensors in vacuum. We need high purity vacuum chambers, and we are also developing vacuum chambers designed for quantum imaging process. Here you see this chamber is where the Skipper-CCD is placed, and here is where we are planning to put the BPO and all the optic stuff. We have several Skipper-CCD detectors because they look different depending on which kind of science you are interested in. And of course, we need ultra low redound noise electronics that I also mentioned, like the LTA board. This is my last slide. This is our space in the physics department. This was the place where the electromagnetism laboratory was used for teaching. Now this lab is in a different place inside the same building, but we have 15 meters square to build up a lab completely dedicated to the research and development of a Skipper-CCD technology in Latin America. And let me say something very, very important. This is only possible because of the very strong collaboration between the physics department and Fermilab. They are the guys who developed this technology, and they are offer us to build up this lab in Argentina to push forward this quantum imaging or quantum information science program. If you are interested in knowing more about Lambda, you can visit this webpage. So my last slide right now is my last slide. Sorry for saying that before. Skipper-CCD has demonstrated being a unique tool for dark matter searches. Sensei, again, has the best exclusion limit for light dark matter, and also for neutrino physics, because there is an experiment with the Skipper-CCD looking for neutrino, but all the calculation we already have done in order to say something about sensitivities, all of them are pretty competitive. The capability of counting electron by electron up to 1,000, 2,000 electrons open a lot of possibilities, and you can think about that. and you probably have new and better ideas. And we are, of course, glad to receive any comment, any suggestion, any point, any field where you think that will be good use skippers. And we have observed the angular correlation between photons. I mentioned that. We are planning our first quantum imaging application using Skipper-CCD for a measure of absorbance in that regime where the Skipper-CCD has something to offer. We have developed the theoretical framework for a dark matter searches through nonlinear optics. And we are building the first Latin American laboratory completely dedicated to this technology. Nonlinear optics will be one of the main subjects, but we are also involved in Violeta, which is the name of the neutrino reactor neutrino experiment, Sensei, the dark matter experiment, CONI, which is also an experiment in Brazil. Carla and I are part of CONI. A lot of collaboration where CCD, Skipper-CCD is the technology to looking for new physics. And of course, as I mentioned before, we are excited to take this sensor to other fields. So if you have any ideas, please feel free to contact us, because we are glad to use these detectors in many fields, as could be a good idea to have this detector working on it. So thank you, obrigado, for this. This is all from my side. Thank you.
Thank you very much. Dario, was very nice, very interesting talk. I would ask people that would like to ask question to raise their hands here at here in the Zoom.
I have a question, João.
Hi, Jorge.
If I can answer. Hi, Dario. So
Yes,
what?
Go ahead.
Yes. So what kind of laser you need to use to create this parametric down conversion? Must be a very fast one, a femto laser, or with a pico laser are you able to work with?
Okay, good question. We are not using a pulse laser. We are using a laser of 405 nanometers. And one important feature is it must be monochromatics. We don't want to have any harmonics. We also, in fact, we have, and we need to get rid of by using filters. So there is no any specific or very difficult condition to satisfy by this laser. It's just a laser. Of course, if you have if I can ask for a laser, I am looking for one monoband laser with a very, very accurate, precise wavelength, but it's nothing special.
So this reduce the cost, because this is really expensive, this femto laser that the other
Yes.
quantum experiment needs, right?
Yes, yes, but in that case, in general, I am not sure, but in general, you are interested in time resolution. Here, we don't have time resolution.
Yeah. So this is the advantage of the CCD, right? Because
Yes.
you are not using one electron and time resolution. Right?
Yes.
Okay.
Okay, thank you. I'll ask now Claudio to ask his question.
Okay, hi. Very quick question, because I have to leave to another meeting. Very nice talk. Thanks a lot.
Thank you. Thank
The
you.
questions I have are, okay, as you do the skipping and you're doing an averaging, you're getting 1/√n reduction in the noise. My question is that equivalent, or is that better or worse than maybe doing a lock-in kind of detection? That means you are going back and forth, so you're locking in between two signals. So if you do an integral in time as you're reading of your voltage reading, would you get a better resolution?
I understand the idea, but I am not sure if I understand completely the implementation of that idea. Something that is very, very important. You must be able to do that in a non-destructive way.
Correctly.
So here we have all the time the same electrons going back and forward. Yes?
Right, but you are reading a voltage.
Yes, but this voltage is the voltage induced by the charge in the other plate of the capacitor. So we put the charge here. I don't know if you are seeing my hands.
Okay, yes.
You put the charge here and you induce charge in the other plate of the capacitors. And you measure the charge here, and you also can read out this. You can get rid of this charge and you move back and forward this charge, but you are measuring all the time the same electrons. This is something creepy.
Right. I understand that. Yeah. Okay.
So if you put this charge in a capacitor and you measure and you move the charge, you know, it's impossible to be sure that you have exactly the same number of electrons, because all the electronics around can produce electrons and can change the original number of electrons you have.
Right. Okay. All right. Thanks. Yeah, I think it is equivalent to, yeah. Okay. I think it's basically
we
the same.
can discuss offline, because probably I didn't understand completely.
Yeah. Okay. And the other question, quick question, is you showed it operates at 120 Kelvin or so.
Yes.
How low do these CCD devices can go?
You can go to nitrogen liquid 77 Kelvin degrees.
But then you have a freeze out as you go towards 4 Kelvin. At which temperature would they freeze the carriers?
No, if you go below, when you go below, you have another effect that you don't want to have. The inefficiency in the charge transfer can increase, and there are another condition that you must satisfy to be able to make the Skipper-CCD and to measure the charge a lot of time. And as you go down, very down, you go high above 106, that condition are not satisfied, and you have, for example, more noise, you have charge transfer inefficiency. Some electrons feel cool and they say, okay, I am good here, I don't want to go to the neighborhood pixel. There are some processes to take into account, but nitrogen liquid temperature was used for this, and it works.
Okay, thanks.
Sorry, Germano?
Oh, yeah, thanks. Actually, my question was also already answered, actually, because I was thinking about the physics of the circuit, the readout circuit. So yeah, I was just wondering, the big difference between the CCD, the regular CCD, is actually the readout circuit that you have for the Skipper-CCD. Yes. So that's basically it, right?
Yes.
Can you apply this technology for any detector? I mean,
no. Yes, but no, because the electronic associated with the readout is in the same Skipper-CCD, in the same CCD. When you build the CCD, you put the amplifiers there. You cannot add a sense node with all this stuff, summing well, output gate, in an existing CCD, because as you can imagine, this is microelectronics. This is very, very sensitive. You cannot put a cable, for example, to connect a specific amplifier connected with a regular CCD. It should be great, but no, it's true what you say. This is exactly the same idea. All is the same as a standard CCD, but the amplifier had this step, and it must be put it in the detector at the same time that the detector is building up. In fact, I can go a little bit more in detail regarding how the Skipper made this process to read the charge. You have, this is the last horizontal, this is the serial register where you have the charge after reading out the pixel, and before entering in the amplifier, you have the summing well, you put the charge here, and you have an output gate and the sense node. The sense node is the place where you are sensing the charge. So you can move the charge in that way. You increase the voltage in the summing well, the charge moves to the output gate and then to the sense node. You sense the charge, you measure the voltage produced by this charge, and then you can move this charge back. This is the forward and back processes that you need to perform in order to measure as many times as you want the charge in a non-destructive way. That part is very important.
Thank you.
And now, Steve.
Hello.
Hello, Steve.
Hi. Thank you for your talk. Very nice, very interesting. I wanted to ask you, well, first, the images of down conversion that you showed, is that the far field of the crystal that you were looking at?
Yes, it's not the ring is not focused on the CCD. Yes, we are seeing in the momentum plane.
Okay. And the second, so you mentioned that there's no timing resolution. And so I was just curious, so how long does it take you to accumulate this image that you're showing here in this slide, for example?
Oh, it's 5 minutes.
Oh, okay.
Yeah, the time involved in taking these images is not because we need to expect a lot to get enough electrons. In fact, we can take images in 5 seconds, but we need, depending on the size of the ring, the readout can take, depending on how many samples you want, several minutes, sometimes 1 hour.
Yeah, I mean, but that, I mean, as far as I know from EM-CCD cameras and the ICD cameras, that doesn't seem like it's too bad. I mean, that seems more or less compatible with the current technology for single photon sensitive cameras, no?
Yeah. In fact, we can use a shutter and just has a very, very low intensity. Just put few photons there, close the shutter, read out the skipper, and then we'll have at most 1 photon per pixel or 0. And in that condition, we have a spatial resolution with the 50 micrometer. We have very high efficiency. I didn't mention, but the efficiency for this wavelength is about 90%.
Okay, that was my third question, but yeah.
Yes, 90%, even better. You have very, very low dark count, less than 1 electron per pixel per day, less. And you have this very nice property that you are able to distinguish between 1, 2, and so on. So yes, in that regime that you suggest, this is the regime where I think this detector had something nice to offer to the quantum information science world.
No, that sounds great. Well, thank you. Congratulations on your laboratory.
Thank you.
Thank you.
Gabo.
Hi, thank you very much for your talk. I'm very glad to see Labotrace converted into the Lambda lab. I was also an undergrad at UBA, and very nice to see how the things are changing there. So I'm very nice your talk, very interesting technology as well, and it's very, very, very surprising to me the efficiency that you have. And my question is related with in the quantum information science, there's also another camera that is called the intensified CCD. You know that those cameras are used to make coincidences. You know, the camera detects the photons, and you can make coincidences with other photons of the down conversion, right?
Okay.
So I would like to know if you have thought about experiments in that direction or something like that.
No, exactly like this. I have heard about that detector, but I am not familiar with the details. In general, all the experiments that include some kind of temporal coincidence, at this step, are out of our goals. However, this is interesting because one of the efforts at Fermilab is going to the CMOS Skipper. It means if you have a Skipper CMOS, you have all these nice features and also you have time resolution. So something that like you are talking about can be done in that regime. But if you have some article or something regarding to the use of this kind of technology, I would like to read about that, because probably we can find, again, some regime in which this technology can be applied.
Yes, for sure. I can send the article for sure.
Right.
And other question, I would like to know the price of those CCDs are, I imagine they are expensive, right?
It's difficult to say because right now these detectors are not commercial.
Okay.
So if you want to have one of these detectors, it must be part of some huge experiment. Sometimes not very huge. Sensei, for example, is producing 100 grams of this detector, which means a lot of them, 50, 100. So it's not easy to find where to produce this detector. There are just one or two places where you can produce these sensors. Berkeley lab is strongly involved in the development of these detectors, but you cannot get one for your lab like something that you can buy in a shop. But you, I think this is now because there are a lot of people looking at this technology like something that can be produced commercially. And I think it's the question of time that it will be available for everybody. I hope so. Everybody hopes so, because this is the idea.
Okay.
So it's difficult to give a price because you need to take into account, okay, I produce 100 of them for a dark matter experiment, then a fraction of them were broken because the processes of putting the wiring bonding, for example, is something very, very critical and very, very hard to do. The people in Fermilab has a lot of expertise doing that. However, sometimes it fails and you lose one detector and it is a lot of money. So I don't know how to put a price. I can give you a price for all of the other elements you need to create one of these systems, but the Skipper itself is difficult to put a price.
Okay. Here, Carla, another Argentinian, is also talking in the chat. So I will talk with her directly.
Okay.
So thank you very much, Dario, and good luck with the lab. And I hope you get a lot of support of this new government and etc. So good luck with the lab. Thank you for your talk.
Thank you so much.
Are there any more questions to Dario? Okay. If not, so thank you very much. Dario, was really very nice, very interesting talk. I hope next time you deliver the next one in Rio and you have the time to have a coffee in person.
I will like that.
Okay. Thank you very much. Take care. Bye-bye.
Bye-bye. Thank you.
Bye. Thanks.
Bye, Dario. Thank you.
Bye. Thank you.
Thanks.
Thank you. Bye.